Hello, everyone. Good evening. Let's get started with our today's lecture. So yesterday we were looking at the block tridiagonal system, and what we said was, we said block tridiagonal system, and we said for this block tridiagonal system solution that we have written, for it to be, for it to not have the round of errors grow, we said the DI, right, should be greater than or equal to sum of the above and the below diagonal elements, right? That's what we said. So this is what we said, where, of course, we realize that each of these A, B, and D are matrices themselves, right? In the case of scalar tridiagonal system, when we have written the Scarborough criteria, we said DI should be greater than or equal to AI plus BI, right? I think this should be valid for all I, and then we said DI is greater than or modulus of this, right? Modulus of this is greater than, and then this should be greater than AI plus BI strictly for at least one row, that is for at least one I. That's what we have written. Now, calculating or obtaining this is not a problem in the case of scalar tridiagonal systems. But when you come to matrices, then how do we calculate this thing, right? Essentially, now you have D as a matrix, then what value should we take to represent it as the norm of this thing? So that is what, so this we represent it as norm, which is basically is what today's topic of discussion is going to be. So we are going to look at how to calculate these values, which is known as the vector norms and matrix norms. Okay, so before that, any questions from yesterday's lecture on the calculation of on the block tridiagonal systems? Okay, maybe as you have, as you show, have these questions, you can stop me. Okay, let us look at vector norms and matrix norms. So in what we're going to learn next is, we're going to look at some kind of iterative methods, okay, later on in the course. Now, in these iterative methods, I mean, we have already seen one application where we need this norm, which is in the context of in the solution of system of linear equations, where we have a matrix and we have to come up with one number that represents this matrix, right? Similarly, another application is where in iterative methods, what we see is that we will see that the error of the method which we calculate should basically, we want this error to decrease from iteration to iteration. Okay. If we want this error to decrease from iteration to iteration, if this error is defined as a single value E, then we can easily calculate that and then show that this is going to decrease. However, let us say if you have a set of values, we have a vector of values whose error we have to calculate. Let us say you're working with some X bar, which is a values of X1, X2, all the way to Xn. Then this X bar is evaluated at one value, one iteration, 1. And then afterwards, it is also evaluated at another iteration, which is Xn at a later iteration. Let us say that is at 2. Okay. So let us say this is also calculated 2. Then how do I, then my error is also going to be a vector, right? It's going to be not just one value, rather it's going to be E1, E2, all the way to En, right? Then how do I use all these values in the vector to come up with a single value with which I can say this is the value of the error, and I can compare this error with the previous iteration value or the and so on, and then say that this is basically the whether the error has increased or decreased. Okay, so that is what is meant by norm, or that is what basically is defined using a vector norm. So basically, vector norm kind of gives you some kind of a size of the vector, so that we can say that this vector is of this much size, and that can be used consistently across the entire calculation. Okay. Excuse me, there must be some. Okay, so sound is stopped now. There is some siren going on for a while. Okay, so size of the vector is what the vector norm basically tells us. Okay, now how do we define these vector norms? So there are again several ways in which these vector norms can be defined, and these are written as follows. The first one is called the L infinity or the infinity norm. Okay, this is written as norm is written using these two parallel lines. And we're going to write this as norm of infinity is basically nothing but maximum value of the modulus of xi. Okay, that's what we're going to say. And then, of course, I goes from 1 less than I less than n. So the maximum value out of the all values that we have in the vector, that's going to give you the infinity norm. That means if you are given a vector, you just simply look at the maximum value and say that this is the L infinity or the infinity norm of this vector. Okay, that is very easy to do. Similarly, we have something called L1 norm, that is called the one norm. One norm is basically represented using these double parallel lines with subscript 1. This is nothing but this is basically summation of all the xi values going from I equals 1 to n. Okay, that is your one norm. So we can actually define something that is known as a p norm for a vector, that is basically x sub p equals sigma I equals 1 to n modulus of xi raised to the power of p. And then for this sum, we take a we raise the sum value to 1 by p. Okay, that is called a p norm. Now, different values can be substituted for p. For example, if you substitute 1, you're going to get whatever I have written on the top. You can also substitute for the L2 norm, which is basically the 2 norm. That is substitute p equals 2. That's going to give you the 2 norm as sigma modulus of xi square I equals 1 to n, and then this is going to be square root of that. Okay, that is going to be your 2 norm and so on. So we can actually define several of these norms like this. Now one might wonder, how am I going to use these norms? Of course, will give you different values. So they are going to give different values depending on which norm would you use. But then, however, let us say if one particular norm comes out to be, or using some particular norm, we may say that the error is decreasing. Then it so happens that all the norms will give you values in the same order of magnitude. Okay. So as a result, we don't have to really worry about which norm we're going to use, but whatever norm we're going to use, that should be consistent across the entire analysis. That is what we should do. We should keep in mind. Okay. Now again, these are few norms that are there in the literature. You can also define, or you can also come up with your own norms to define for vector, norm of vector. But then all these norms that are there and that may be defined in future should satisfy. They should satisfy the following properties. Following properties. What are those? The first one is that the norm of the vector is greater than 0 for all x bar that is not equal to 0 bar. That means if you have a vector that is not a null vector, then the norm of that should always be greater than or equal to 0. Okay, should always be greater than 0, not equal to 0, greater than 0. And then if you multiply the vector with a norm, if you multiply the vector with a constant, and that should be equal to the modulus of k times the norm of that vector. Okay, so that means if you multiply the entire vector with some constant k, whether positive or negative, it is equal to the modulus of k times the norm of the vector. That is the second condition that the norm that we define, whether it is an infinity norm, 2 norm, 1 norm, and so on, should satisfy, or any other new norm that you kind of define in future. Okay. Similarly, the sum of the norm of the sum of the vectors is less than or equal to sum of the norms of the vector. Okay. So the norm of the sum of the vectors is less than or equal to sum of the norms of the vector. That means norm of x plus y is less than or equal to norm of x plus norm of y. Okay. So this is the so these are all vectors. So I'm going to put x bar, y bar, and so on. Okay. So these are the conditions which the vector norms should satisfy. Okay. The existing norms as well as any future norms that you wish to define. Now, with this, we can easily calculate, given a vector, we can always apply and calculate what is the 1 norm, 2 norm, and so on. Okay. Questions on this so far? Okay. Looks like I think you're all okay
This is
with
okay,
this.
sir. Okay, sir.
Yeah.
So we can proceed. So again, we'll come back after repeating this lecture.
Okay,
But
fine. Yeah.
primarily it's understood, sir. Not a big issue in that.
Sure. Yeah. Okay. Fine. So let's move on. Let's move on to the matrix norms. So just like the way we have defined the vector norms, let's look at matrix norms. What are matrix norms? Now, matrix norms are essentially in a similar spirit as vector norms. They are defined. However, they are slightly different. Now, the need for matrix norms arises. Need for these norms arises. Need for matrix norms arises when we try to ask the following questions. Arises when we try to ask the following questions. Okay, so what are those? Let us say we have a matrix. We wish to solve, let us say AX equals B. Okay, that is what we wish to solve. So under what conditions can we solve AX equals B? Well, that means, can we solve AX equal to B always? If some matrix is there and then it is multiplying some with some vector, can we always solve for a given right hand side this vector unknown X? Okay, and then how stable is the solution X bar for small changes in the right hand side vector, that is B bar. That means if we're going to perturb B, okay, we're going to perturb B, then how does the solution of X bar going to be changed? That means we want to change B bar to some B tilde bar, slightly perturbed. Then how much does the solution change? Is it going to be also change in a similar way? Like let's say if this B is perturbed with a small amount, will X bar also going to change by a small amount, or is it going to change by a large amount? So, and then under what conditions can we solve AX equal to B? Let's say we are given AX equal to B. What are the conditions in which we can solve this? So these are the two questions which lead to defining something that is known as a condition number. But before that, we look at what is a matrix norm. Okay, so these are the questions that lead to what is a matrix norm. So matrix norms, just like the way we have defined vector norms, can be defined as follows. Now we realize that A is a matrix. That's basically A of ij. Okay, so we can define something known as the infinity norm. Okay, which is the L infinity. L infinity. It is how this is how it is denoted. This is called the L infinity norm or infinity norm for a matrix as a norm of A sub infinity equals, this is basically modulus of Aij sum over all the columns j equals 1 to n, and then take the maximum value of that. That means I less than or equal to n. So what we're trying to do is that this is basically the maximum column sum. Okay, so this is the maximum column sum. That means once we are given a matrix, we're going to, let's say we have certain values. Okay, then what we're going to do is that we want to sum all these values in this column. Then we're going to sum all the values in these columns. And then we're going to sum all these values in this column. And then we're going to take the maximum value out of all these. That means, let us say this sum came out to be some value. And then let's say this sum came out to be some value. And then this sum came out to be some value. Then we're going to take maximum out of all these values, right? That's what we're going to look. That means we're going to sum all the, for every I, I'm going to sum all the j values, right? I'm going to sum all these things, and then I'm going to calculate what is the maximum in an absolute sense. Okay, that means we're going to apply absolute for all of these things. That means even if you have plus or minus, we're going to take only the absolute value. That is called, also known as the maximum column sum. That is called the infinity norm. Okay. Similarly, there are other norms, just like the way we have defined. So these are slightly different from the vector norms. Then we have
I have a question over here.
Sure.
So just you told that how efficient the solution is, like that will be checked by if you perturb the value of the A.
B.
Then B. then how my X is varying large or not in that way, right, sir?
Correct, correct.
So my point is, yes, sir. For example, when I'm solving AX is equal to B,
Hmm.
that means for a given value of A, I'll be always be getting a fixed value of A, right, sir?
No. For a
For
given value of A, we're going to
value
get.
of A, fixed value of X actually.
So for a given value of A and B, you're going to get certain value of X.
X, right, sir. Like
Correct.
for example, like x square minus 4x plus 4 is equal to 0. That means x minus 2 whole square is equal to 0. Then I will get the x value of x is equal to 2. Now, if
Correct.
I perturb the value of x, then I will never get a solution, a root of the equation in that way.
Yeah.
So my point is that then if I am perturbing the value of A, or
Not
like
not the value of A, the value of B
sorry,
bar. Yeah.
B bar, if
Yeah.
I'm then the x will be different for sure.
Right. It is
So-
different for sure, but is it going to be very different, or is it going to be still in the neighborhood of the previous X? For example, let us say you have changed your B bar by 1%. Right?
Okay.
You have some value, so you increase your B bar by 1%. Then how much will the X bar change? Will it also change by 1%, or will it change by 10%, or something like that? That's what we are interested in.
So
Now,
that will depend. That will depend on, sir, how the in which relation this function exists. Suppose it is in polynomial form, or it may be in linear form. If it is in linear form, it will not be varying so much. But if in polynomial form, it will vary very high in that way. Then how will decide in that sense?
No. So right now we are actually looking at only linear equations. For example, A contains all constant values. So as a result, it is linear combination of all these x's, right? Even then, I will show you a little later with an example that depending on the properties of A, this solution can actually change very greatly for small perturbations in B. So that is what this A matrix or the properties of A kind of decide. In fact, we will see that the solution we obtain may not even be a solution to that problem that is given to us. So that means we have to be very cautious about the solution we obtain, and then we have to always verify the solution with the properties of A. Is the matrix A nice enough or conditioned enough that the solution I obtained is correct or not? So we are only talking about linear system of solutions, linear system of equations. Even then, depending on the properties of A, the solution X can be very different from the properties of from if you have changed B by a small value. It is possible.
Okay.
We'll see that.
Okay.
Yeah, I mean, I get your point that if you have a nonlinear, quadratic or cubic or some polynomial form, then you are going to get, even for a small change in X values, is going to give you a large change. That is true. But then we have not even gone to solution to nonlinear equations. We are still looking in system of linear equations, right? Where everything is linear.
Okay. Thank you for the clarification, sir.
Yeah. So essentially, we are still looking at 2x plus 3y equals some 5 and so on, right? Everything is linear.
Noted, sir.
Yeah. Yeah. We will see that in a little while. Any other questions, anybody? So let's define what is L1 norm. That is called the 1 norm. This is also similar lines to what I have written above. This is called 1 norm. This is maximum of 1 less than or equals j less than or equals n modulus of, or the sum of I going from 1 to n modulus of aij. Okay, so this is basically can be thought of as the opposite of what we have written here. This is called the maximum row sum. That means we are going to sum all the row values. That means we're going to sum all the row values and then take the maximum in the column direction. That means we're going to sum all these rows, right? We're going to sum all these rows and then all these rows, and so on. And then eventually we're going to take whatever we get here, we're going to take maximum out of these values. Okay, that is going to be your maximum row sum. That is also known as the 1 norm. Okay, so that is the 1 norm. If we were to kind of depict it here. Then we have something known as the L2 norm. So these are slightly different. So L2 norm is the 2 norm of a matrix. So this 2 norm of a matrix is kind of very different. This is basically equal to the square root of R sigma of A transpose A. Okay, so essentially what this means is that this is basically nothing but R sigma is also known as the spectral radius of a matrix. That means if I'm calculating, so that means I'm given A matrix, I'm taking A transpose A, which is also a matrix. and I'm calculating the eigenvalues of that matrix. Okay, so spectral radius basically of a matrix means that this is the maximum absolute eigenvalue of a matrix. Okay, I hope all of you are familiar with the concept of eigenvalue. Given a matrix, what is an eigenvalue, right? Given a matrix, how do we go about calculating eigenvalues? Let's say matrix is given, then you essentially you say that A minus lambda I, the determinant equal to 0, and then that's going to give you a characteristic equation. And that characteristic equation, if you solve, it's going to give you the values of lambda 1, lambda 2, and so on, right? And then you take the maximum absolute value out of all these things, and then you plug it in and then take a square root of that. That is going to be your 2 norm. So this is kind of somewhat different from what we have learned before, okay, in the vector norms. So that is the and then in this case we are taking so spectral radius of a matrix is the maximum absolute eigenvalue of a matrix. In this case, the matrix we are considering is A transpose A, not just A, it is A transpose A. Okay, that's going to give you the 2 norm. Okay, of course, eigenvalues are kind of very important phenomena. We will come back to it later whenever to discuss something. Okay, then there is also another norm called Frobenius norm. Which is basically slightly different. It is denoted as A sub f. This is equal to modulus of Aij square sum over j equals 1 to m, sum over I equals 1 to m, and then square root of that. Okay, that is your Frobenius norm. This seems to be somewhat similar to the 2 norm, which is the Euclidean norm, they call it. But then this is different. Okay, this is different. This is not the 2 norm. This is the Frobenius norm. So people use this Frobenius norm because it is it's actually very easy to calculate. That's why people use the Frobenius norm. That means, again, just like the vector norms, we can use any of these norms to define the size of a matrix. Okay, to get some representation for what is the size of the matrix, we will use any of these norms that we have defined before. Okay. Okay, now we have still not answered the question. The 2 questions we have raised, we will answer them shortly. Before that, any questions? Okay, yeah.
No, sir. Please proceed.
No, fine. Okay, all right. So then we define something that is known as a. We have something we define. Let us say we want to solve for Ax equals b. Okay, that is why we want to solve. Then we define something called a condition number. Okay, and the condition number of the matrix A. Okay, which is represented as you can write it as condition number of A. It is also denoted as some k of A. Okay, and this appears that this condition number plays an important role in determining the whether we will be able to solve Ax equal to b or not, and also how sensitive or not, and also how sensitive our solution is going to be for small changes in the right hand side vector b. Okay, so apparently these 2 questions that we have raised are related to something that is known as condition number. Okay, and that is what we're going to look at. So condition number is basically k of A is defined as the norm of the matrix A times the same norm calculated for A inverse. That means if you're going to write it for, let us say, 2 norm, it should be for 2 norm. Let's say if you're going to write it for 1 norm, it should be for 1 norm. Okay, something like this. Or this is also equal to norm of 2 times norm of A inverse 2. That means, let's say this is condition number based on 1 norm. Similarly, condition number based on 2 norm is this thing, and so on. So we could define condition numbers as the norm of the matrix A times the norm of the matrix inverse Okay. Again, it turns out we don't have to actually, we don't need to calculate A inverse all the time, wherein we can use we can make use of, we can use another definition for condition number, which I will kind of inform in a little while. Okay, so in which case we don't have to use calculate A inverse all the time. But then of course this other definition which we're going to look at is going to involve the eigenvalue, so we have to calculate the eigenvalues in that case, if not the A inverses. Okay. Now again, this condition number is something, it will basically come out to be some value, right? Because this norm is going to give you one value. Similarly, the norm of the A inverse is also going to give you one value. When you multiply these two numbers, you're going to get some number. Now, if this condition number is large, then we call this system as ill-conditioned. That means we're going to call this AX equals B as an, or matrix A as an ill-conditioned matrix, and this is small, we're going to call it as well-conditioned. Okay. Now, what does it mean? That means, let us say I want to solve for, so if K of A is large, let us say if K of A equals some, can be represented using, let us say it is some 10 square, 10 power 5, something like that. Then if we can write it as 10 power K, then we are going to lose K digits in the calculation, of AX equal to B. Okay, so let us say if it is large, for example, let us say 10 to the 4, then we're going to lose 4 significant digits in the calculation of AX equal to B by any method. So that means the solution is not going to be accurate. Let us say if you are working with very small numbers, then losing so many digits will basically make your calculation give you incorrect results. Okay, so that is the problem. So as long as, that means as long as our condition number is not or the K is not smaller than, as long as it is smaller than the precision of the computer that we can represent, then still things are okay. But if the precision of the computer is not smaller than this value or larger than this value, then we're going to have problems, right? Because if K happens to be larger than the precision of the computer, then we're going to lose all the significant digits, and then the solution is not going to be accurate. Okay, so that is the thing. So let us look at perturbation of the equation. So we said A times X equals B. This is the equation we want to solve. Now let me perturb the right hand side a little bit. Let me write it as B plus delta B. I want to perturb the right hand side. Let me call this solution, new solution, as, let us say, changed it to A times X plus delta X is the new solution that we would obtain if we were to solve for B plus delta B. Okay, so this is the initial solution. This is the perturbed thing. Okay, this is the original system, and this is the perturbed system. Okay, this is the perturbed system. Now I can also write this as, oh, I forgot to write the matrix conditions for the matrix norms. Okay, so let me also write the conditions for matrix norms and come back to this, just like the way we have written for the so the matrix norms follows these following conditions. Matrix norms conditions, just like the way we have written the vector norm conditions. So the condition number of identity matrix would be equal to 1. Okay, that means the norm, the norm of the identity matrix will come out to be 1. And then when you multiply with A times X, okay, some vector A times X will be less than or equal to norm of A times norm of X. Similarly, when you multiply A with some matrix B, then it is going to be the norm of the product of the two matrices will come out to be less than norm of the matrix A times norm of the matrix B. Okay, so these are the some conditions which all the norms that we have defined, whether it is 1 to infinity or the Frobenius norm, will have to satisfy these conditions, or any other new norms that you may define also need to satisfy these conditions. Okay, then only we can call this norm as a matrix norm, otherwise we cannot call it. Okay, now let's go back to our discussion that we have AX equal to B as our original system, and then I'm going to perturb this slightly. Now, we may wonder, why are we perturbing this thing? Now, this is very relevant because let us say you are getting all this system of equations from some measurements. Okay, you're doing some measurements in the lab and you're getting it. So there are certainly some errors associated in the measurement, right? So these errors are there, or these could be coming from either from errors in the lab measurements, right? It is always not possible to get exact value. There is some plus minus value. Similarly, these round errors could be coming from a round of errors. Let us say if you have done some simulation and got these values, then this B itself is already having these round of errors, right? There are some errors that are already built into the B. Okay, so that is why this B is not exactly that value that we wish to solve, but it is slightly perturbed from the B value, right? So that is why we are trying to perturb the system. Then what we have is, when I look at A times X plus delta X equals B plus delta B, I can write this as A times X plus A times delta X equals B plus delta B. Then we know that essentially AX equals B, right? So these two can be cancelled on both sides. Then what we end up with is A times delta X equals delta B. That's what I have, right? This is what I have. So I can write this as delta X equals A inverse delta B. Okay. Then I can take the norms of this thing. So I can say norm of delta X equals norm of A inverse times delta B. Okay. But I know that the norm of A inverse times delta B is less than or equal to norm of A inverse times norm of delta B, right? That means norm of delta X is less than or equal to norm of A inverse times norm of delta B. Okay, so that is, let me call it as equation 1. And then our original equation is basically A times X equals B. Okay, A times X bar equals B bar or something. That is the original equation. Here also I can apply the norms, right? I can apply norm of B equals norm of A times X. But then I know that this is basically less than norm of A times norm of X, right? That means norm B is less than or equal to norm of A times norm of X. That is the second equation I have. B, okay. So we have delta X. What did I write? Okay, so A times delta X equals delta B. I got delta X here. This is inverse. Delta X, okay. So we have delta X is this thing. Mod B. I want to write this as, okay. So we have, I want to put it in a slightly different way. A times delta X is this. Okay. Let me not write, let me slightly do it differently. I want to keep delta B is this thing. Okay. AX equals B. A times X. Okay. Okay. So let me go back and write what is, okay, here I can write this slightly differently as 1 by norm of X is now less than or equal to, right, norm of A times norm of 1 by B. Okay, that is my second equation I want to use. Okay, I'm rephrasing this equation to be like this. So that's what I got. 1 by norm of X, I'm sending this guy to the left hand side and this guy to the right hand side, okay, which is giving me this quantity. Okay, I think then I can now divide the first equation divided by second equation. That's going to give me delta X divided by X. Okay, so that's going to be norm of delta X divided by norm of X is going to be less than or equal to, I'm going to just multiply 1 times 2. Okay, that is delta X divided by 1 by delta X equals norm of A times norm of A inverse. So multiply 1 with 2 because there is already 1 by delta X here. And then on the right hand side, what I have is delta B norm, that is delta B norm divided by B. Okay. Now, what is this value? This value is basically delta X by X less than or equal to, this is nothing but your condition number of A in some norm times you have delta B norm divided by B norm. Okay. So that means you can clearly see here, if I perturb my right hand side, if delta B is perturbed with respect to B, so this is the some kind of a perturbed or a percentage perturbed value, then how much the delta X changes is determined by the condition number. That means if the condition number is small, then this change will translate into pretty much the same value into the solution X. Whereas if my condition number is large, then if I have perturbed it by a small amount, then the solution is going to change by a large amount, right? It's going to get amplified by so much value. That means if my condition number is 10 to the 4 or 10 to the 5 or something, then my solution, which is delta X, is now going to change so drastically. Okay, so that is the idea by which we can now use Ka to tell us if the solution is going to change drastically or not. Now we are in a position to answer the questions. So these are essentially, in principle or in theory, Ax equal to B can be solved if condition number of A is not equal to infinity. However, in practice, we can solve Ax equal to B if Ka is not too large, right? If it is not too large, then only we can solve it correctly, because the solution we obtain from Gaussian elimination or some other method may not be correct if the condition number is very large. Okay, it may be ridden with errors because we're going to lose significant digits while we are proceeding, right? Similarly, we can answer the second question. Second question was how sensitive the right hand side is going to be. Similarly, if Ka is small, then the changes in X are going to be small. If Ka is large, then X may change significantly compared to original solution. Okay, so that is the idea. Now, okay, that is the idea. Now, what does it mean? That means that let me kind of give you an example. Before that, let me give you another way to calculate the condition number, which is another way to calculate condition number is basically equal to the ratio of maximum. So once we calculate the eigenvalues for a matrix A, the lambda max absolute value divided by the lambda min, okay, can also be used to calculate what is the condition number. Okay, this is it kind of comes out approximately to the 2 norm. Okay, so this can be used to calculate the condition number. So that means if we can calculate the eigenvalues, where lambdas are the eigenvalues of matrix A. Okay, so if we calculate the eigenvalues here, you look at the maximum absolute value and then the minimum value, and then you take the ratio of these two. That's going to give you the condition number. So in that sense, we don't have to calculate the A inverse as such. But if it is asked in the question that we have to calculate the condition number based on infinity or 1 norm, then we have to calculate the A inverse and then only find the condition number. Okay, so let us look at a couple of problems. So let me say first problem is, consider the linear system. We have 7x1 plus 10x2 equals something on the right hand side, B1, and then we have 5x1 plus 7x2 equals B2. So we have this system where B1, B2 are right now not specified, but then we want to first calculate the condition number for this thing, and then we want to perturb this right hand side and see how the solution x1, x2 is going to change when we perturb this system. Okay, so that means first let us calculate the condition number based on the infinity, 1 and the 2 norms. Okay, and then we try solving B1, B2 for 2 different right hand sides. Okay, so let me first calculate based on this thing. So my A matrix is going to be 7, 10, 5 and 7. Okay, this is kind of pretty symmetric. I mean, symmetric in a sense, this is pretty much the same. So what will be the infinity norm? So L infinity norm is going to be how much? This is going to be the maximum column sum. That's going to be maximum of 10 plus 7, 17, and then 7 plus 5, 12. This is going to be 17, okay, for the A matrix. Similarly, we can also calculate what is A inverse. A inverse is going to be 1 upon AD minus BC, that is 47 sevens, 49 minus 50, that's going to be 1 by minus 1 times D minus B minus C A. Okay, so A inverse is going to be minus 7, 10, 5, and minus 7. Okay, then I can also calculate what is L infinity for A inverse. Right, that is the condition, that is the L infinity norm for the A inverse matrix. That's going to be maximum of, again, 10 plus 7, 17, and then this is going to be 12, this is again 17. That means my condition number based on infinity norm for the matrix A is going to be L infinity A times L infinity of A inverse, or this can also be written as norm of A in infinity times norm of A inverse in infinity. That is nothing but 17 times 17, that's going to be 289. Okay, 289 is quite large, it's already 200. Like, we wish to have the condition number as close as possible to 1 or maximum less than 10. Okay. Similarly, I can also calculate it from the other means. For example, I can calculate what is the norm of A, one norm of A, that is going to be the maximum row sum, right? That means we're going to sum the rows. That is again maximum of, for A, it's going to be 7 plus 5, 12, and this is going to be 17. So we have maximum of 12 comma 17. It comes out to be 17. Similarly, one norm of A inverse is going to be maximum of the sum of the rows. That's going to be a modulus of 7, minus 7 and 5. That's going to be 12, and then 17. This is going to be again 17. So as a result, the condition number of one norm of A is going to be norm of A in 1 times norm of A inverse in 1. That's going to be also 289. Okay. Now, you can also calculate what is the eigenvalues of this problem. Okay. And then calculate the K2 of A to be lambda max divided by lambda min. Okay. That will also come out to be around 200. Okay. That you can calculate. So this you can calculate later. So that means, how do I do that? We have this matrix. So A minus lambda I equal to 0. That means we're going to write it as 7 minus lambda, 10, 5, 7 minus lambda, modulus equal to 0. That's going to give you 7 minus lambda whole square minus 50 equals 0. I think I'm ending up doing this thing. So 49 plus lambda square minus 14 lambda minus 50 equals 0. So what you have is lambda square minus 14 lambda minus 1 equals 0. Okay. So essentially what you get is, you get lambda equals minus b plus or minus square root of b square minus 4ac by 2a. Okay, we're going to get something 14 plus or minus square root of 14 square plus 4. That is how much? 256. 256 plus 4, 260 is it? I think it is 260 by 2. Okay, so essentially we're going to get some, this is going to be 7 plus or minus 4. 4 is going to be 45 or something. So you're going to get some value here. Okay.
16.12, sir. 16.12 divided by 2.
16.12 divided.
7. So 14 plus minus, you can write, so 14 plus minus 16.12 divided by 2. Simple.
Okay, that is some 8 point something.
Yeah, 8.06.
8.06. That is some, you'll get some value. Okay. So I think it may be different from this thing. 14 by 2a. Okay. Okay, you can check that. So this will also come out to be few hundreds. Okay, the lambda max my lambda win also will come out to be few hundreds. Then essentially the point here is that now, because this is already large, okay, if you take the b1 b2 to be equal to 1 comma 0.7, okay, 1 and 0.7, and solve for the values, then you're going to get x1 x2 from ax equal to b. You're going to get this as 0 and 0.1. Okay, you're going to get 0 and 0.1. Whereas now, if I perturb the system, instead of b1 b2 to be 1 and 0.1, I take it slightly perturb it, like add 0.01 to the top. Let me make it as 1.01. Reduce this by 0.01. Okay, that means let me make it 0.69. This is a very small change, which is representative of some error in the measurement or round off error and so on, which is very natural. Okay, so in this case we got 0 and 0.1. Whereas, which we have just changed the system, the right-hand side with a very small value, then the right-hand side value, if you calculate, you're going to get this as minus 0.17, and then you're going to get this as plus 0.22. You need to solve for Ax equal to B. Now, what you see is that this is a large change compared to a small change in the right-hand side. This is happening because of the condition number being large. Okay. Now, why is this so much useful? Is because, or why is this happening? So this is you can think of it in 2D as like this. For example, let's say in 2 dimensions. Let us say, or before that, let me say one thing. So the condition number of the identity matrix, will be equal to 1, and the condition number of a matrix A that is close to singular is going to be infinity. Okay, that means if you have a singular matrix, that means it is the condition number will come out to be infinity. But then condition number of an identity matrix will come out to be 1. So we want to keep as small as possible condition number, because the solution we obtain will be correct. Otherwise the round off errors are kind of dominate and the solution is not going to be correct. Now, let me give you another example. So if we take another example, let us say second example is I have 0.1036x plus 0.2122y equals 0.7381, and the second equation is 0.2081x plus 0.4247y equals 0.9327. Okay, now if you see this system, unlike the previous case where not the previous case, some time back we looked at pivoting in the Gaussian elimination, wherein we said if the elements are varying over orders of magnitude, like if you have one element in the 0.1, 0.2 like that, and then other element is in hundreds or something, then we said this is going to change. So we wanted to keep the largest possible element as the pivot and then do the calculations, because that is going to reduce the accumulation or truncation errors, right? Round off errors and so on, or round off errors. So, but in this case, if you see, there are no such problems, right? All the elements are of the order of 10 to the minus 1. So there is no problem. But then if you calculate the condition number for this matrix, okay, that will come out to be of the order of a few thousands. It will something like 1700 or something like that. Okay. Let's say based on the eigenvalues. So this is actually quite large. What this means is that, let us say if you try to do this problem with, if you try to solve this for these two equations using, let us say you use 3 digits as the 3 significant digits only you want to keep. Okay, your calculation can only handle 3 significant digits. Then the y value that you would get would be equal to minus 547. Now let us say, now if you have done the calculation with 3 significant digits, your y value is minus 547. We think it is correct and go back and use it, but it turns out it doesn't satisfy these equations. So if you go back and do the calculation with 4 digits, okay, and then redo the entire calculation of Ax equal to B, that's going to give you y value to be equal to 343. This is completely different, right? Compared to minus 547, we are switching from minus 500 to 340. If you with just one more digit extra, and then if you do it with 10 digits, what you're going to see is that the y value actually comes out to be close to 346. Okay, this is not too bad compared to 4 digits, but at least somewhat it is still different. So that is what you get. Now this is happening because of the large value of the condition number. That means this matrix is now has a large value. As a result, the solution you're getting is very prone to the number of digits that you are using in representing the round of errors. Okay, in rounding them off. So as a result, we have to be very careful when we try to do these calculations. And if the condition number is large, that means the solution need not be guaranteed to be correct. You have to go back and check, is the solution satisfying my problem or not? Okay, that's what we need to check. Now, to think about this from a geometric perspective, we can always draw these 2 lines as essentially they are 2 lines, right? Ax equal to, so this is more like Ax plus By equals some value, and then the next one is also some Mx plus Ny equals some Q. Okay, these are 2 lines in 2D. So we also know that these 2 lines actually become, if the matrix becomes singular, that means these 2 lines kind of collapse onto one another, like they are parallel to each other. Only then the matrix can become singular. That means what happens is if these two lines can be represented something like this. Okay, let us say these are the two lines we are trying to solve in 2D. Okay, then we realize that because of the way when we do experiments or something, there could be some measurement errors. That means, let us say this is the okay. Let us say because of the way we are measuring things, there can be measurement errors, and this could be perturbed slightly. So this line may not be exactly the straight line I have drawn. It could be anywhere between these two dashed lines. Similarly, this line could be anywhere between these dashed lines because of either round-off errors or experimental errors and so on. So as a result, when we try to solve the system, instead of getting the solution as here, we will get the solution which is basically going to be essentially in this zone, okay, in the entire square or rectangle we have drawn here. Now let us say, but then so that is the solution. It's going to be within this zone. Now let us say if these lines are if these lines are kind of somewhat parallel to each other, okay, so we have this line, and then the other line is something like this. Okay, this is tending to be parallel to this line. In which case, if we have errors, so these errors are going to be essentially going to be like that, right? So that is going to be the error, same as before, and this is going to be the error, which is same as before. Okay. Now in this case, what you see is that this region of where these errors is now much more amplified, right, than this one. Okay. As it becomes closer and closer, this is going to become more and more amplified, right? And as a result, it's going to result in more uncertainty. That means the solution is not going to be this one. Rather, the solution can be anywhere in this, depending on the round-off errors. So that is the problem with large condition numbers. So this is one way to think about that the solution may not be accurate for large condition numbers. Okay. So ideally, we would like to keep it as we would like to solve when the system is as close as possible to one. Now that raises concern. For example, let us say, what if my system has a very large condition number? That means we have to again come back and check if it is large. We have to use several digits in the calculations. Even if that is not going to be satisfying the original system, then we have to go for other methods such as least square based solution algorithms, where we are not going to satisfy this in a point manner. Rather, we're going to satisfy the solution of these lines in a least square sense. So we're going to try to minimize the error in a least square sense. Okay. So that is what we have to do in case if the condition number is very large. But then if the condition number is very large, that means it is not possible to solve it. Like, in the limit, if it is infinity, the solution you get is, there is no solution because the system is singular, right? So that is the kind of geometric way to think about the condition numbers and the norms of the matrices. Okay. So with these two examples, I'm going to stop here. This also finishes the first chapter, that is solution to system of linear equations. So tomorrow we'll start afresh with the second chapter, that is solution to nonlinear equations, and then followed by solution to system of nonlinear equations. Okay, that is going to be much more easier than the first chapter because we do not have matrices. We are going to just deal with single equations, and then of course when you go to system of nonlinear equations, you're going to have matrices again, but that should be manageable. Okay, compared to this. Now, any questions? And then if you are ready with the MATLAB installations and all, I would like to give you the assignment. Maybe I will give you tomorrow so that you can start working on it. Okay, any questions so far on today's lecture?
It seems okay, sir. Yeah.
Okay, it is okay, fine.
But again, we have to just
you have to go
the
through that again. Yeah. Sure. I would suggest you calculate all the norms, condition numbers for different matrices and so on. Okay, I'll also give you some, in the assignments, I'll also give you some problems. Yeah.
Thank you, sir.
Thank you. Any questions, anybody else?
Sir, am I audible?
Yeah, please go ahead.
This condition numbers and the matrix norm, in terms of, say, for example, the background calculation of, say, a solver, If you're doing, say, NFEA,
Mhm.
how does this error computation reflect there in terms of where the solver is running and how it is processing it? Just want to understand the
Yeah, so it may so happen that, I mean, the solution we get may not be accurate. I mean, in your FEA solver, you might be solving for AX equal to B several times, right? So, but we want to make sure that this matrix is not close to singular. Okay. If this is close to singular, then it is possible that the solutions you're getting are not correct. Because if you go back and substitute, they are not going to satisfy the right answer. Now, one way to think about it is that if it is so, then eventually, let us say if you are doing some transient simulation or something, eventually it may diverge, because the solution is not going to satisfy at this stage. And if this is fed to the next level of iterations and next level of time step and so on, then eventually it is going to, the solution is going to diverge rather than converge to a single value, right? So this thing can happen. If that happens, we have to go back and see that the reason is because A is not a well-conditioned matrix.
Okay.
Yeah, it is not very straightforward to figure out, but then you have to make sure that A is well-conditioned. That means its condition number is small. That means the system of equations we are trying to solve are not close to singular system, right?
Understood.
Yeah, if it is close to singular, that means there is something wrong with it. That means close to singular means you have, it means that you have two lines that are parallel in a 2D, or you have one equation is very similar to the other equation in terms of coefficients.
Got it.
Yeah.
But that will not be the case in some physical, mechanical related problems, right?
It should not be. Even in FEA, it should not be. But then it is very much also possible, depending on discretization, depending on other errors, that you may get singular systems.
Okay, so just one more follow-up question. This, say, for example, it is known that like the choice of norm can actually impact the sensitivity of the matrix. How we assess it and how sensitive it is. Like how is the norm actually chosen? Like this is the norm with which you assess it.
Okay, so it doesn't matter. You can pick any norm. So as I said, all the norms will give you in the same ballpark number. We can pick either the the one norm or the two norm. Typically the two norm is the most widely used. But any other norm also can be picked. I mean, essentially, if it is going to give you, if the condition number is large based on one norm, it is going to be large based on any other norm as well. Okay, it will be in a similar range. It may not be exactly equal, but if let us say one norm gives you as order 10 power 3, then the two norm also will give you order 10 power 3 and so on.
Oh, sorry,
so you can pick any norm.
There was a network issue. Sorry, can you please repeat?
No. All I'm saying is that there is no hard and fast rule that this norm should be picked. The second norm is the most widely used, two norm. Okay, but then all the norms are going to give you in the same ballpark. For example, one norm gives you of the order of 10 power 3 for the condition number. Your condition number based on two norm also will give you in the same order as order 10 power 3. For example, this could be 2000, this could be some 4000 or something. Okay, they are still in thousands, which basically means that the condition number is not small. Okay, so any norm can be used, but that should be consistent.
Okay.
Yeah. Both in the context of vector norms as well as in the matrix norms.
Okay. Got it. Thank you.
Yeah, thank you. Any other questions, anybody? Okay, if not, I'm going to stop here. I'll see you guys tomorrow at 4 o'clock. Okay, we'll meet at 4 o'clock. Yeah.
Okay, thank you, sir.
Thank you.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you,
sir.
Thank you, everybody.
Thank you, sir.
Thank you.